Hi everyone. In this lecture we are going to talk about wedge product and differential n forms. So in our previous lectures we saw that a differential one form is such an object that it takes a vector n and spits out a number. In other words, if you want to see it geometrically, what it does is that it takes a vector and it finds out the projection of the different bases. That means along some certain basis what is the projection of that vector. So if we recall that, that means what one forms did is that one forms or differential one forms found projections of vectors along a basis or an axis, whatever you want to call it. So what we want to do right now is that we want to define a differential two form. So we want to define a differential two form. So how this two form will look like, we'll come to that later, but from the fact that one forms find out projections gives us an idea that if you consider a vector, let's say in a 3D space like this, and if you take the projections onto the different axes, so this is the, let's say, x projection, this is the y projection, and this is your z projection. So this one forms take this vector and finds out these projections, and if you just look at one of these axes, that means that the projections are equal to some certain length, right? And this length can be thought of as a one-dimensional volume. So these projections can be thought of as 1D volume because you can only move to left or right. So the only dimension you get is the length, and you can think of it as a one-dimensional volume. So what we want to do right now is that we want the differential two forms to show some certain property like differential one forms. That means what it will do is that it will give us some information about a two-dimensional volume of some pair of vectors. Why I'm using a pair of vector? Because if I use only one vector, I cannot generate a two-dimensional volume. That means an area. I have to take at least two vectors, and I can even do it with more vectors, but then I'll have to just slice. I'll have to take a slice of that higher dimensional volume to get a two-dimensional volume. Okay, so we want the differential two forms to show some volume invariant properties. This will be a 2D volume invariant properties. Just like one forms. Oops, sorry. I think I just got bugged out. Yeah. Okay. Here it is. Properties. So as I was saying that it will show some 2D volume invariant properties just like the one forms. Oops. Yellow color. And with that in mind, we write our first differential two form as follows. So this is a differential 2 form. So let's say you have a vector like this and another vector like this, and obviously you can think that there is a parallel, these vectors will span a parallelepiped like this, and let's say this is your x, this is your y, this is your z, and if you want to show, or if you want to find out the projection of this area along the xy plane, you can do that with a differential 2 form, because here you not only you have to find out the projection onto the x-axis and y-axis, you also have to multiply them in the Euclidean geometric sense. So this differential 2 form is written as, let's say, dx, and there is this symbol dy like this, and this symbol represents a wedge product. So this is a wedge product of one forms, a wedge product of one forms. You might ask, what is this wedge product? You can think of it as a generalization of the cross product that you see in your 3D space. Cross product doesn't exist for higher dimensional spaces. However, the cross product itself is a special case of this wedge product. And how do you work with wedge product? Since we will be considering ourselves with areas and volumes, and we already know the determinant and cross products are related with the area and the volume, because if you take a cross product, at the end of the day you have to take some determinant to get the scalar volume, right? So this motivates us to define this differential 2 form as follows. So this differential 2 form will act on this pair of vectors. Let's say this is v, this is w. If they act on this pair of vectors, it will give you dx of v, dx of w, dy of v, dy of w, like this. And if you consider v to be, for this case you can think of it as a 3-dimensional vector, let's say v1, v2, v3, and w to be as w1, w2, w3, you can immediately say that these are just one forms that you saw in your previous lectures, and immediately you can write that this is just v1, w1, v2, w2. That means the determinant v1, w2 minus v2, w1. This is how you deal with a differential 2 form. And one thing to note is that this differential 2 form shows antisymmetry. That means that dx wedge of dy is equals to minus of, sorry, it's not minus, that means when you switch them, that means dx dy is not equals to minus dy dx, rather dx dy is equals to minus dy dx. So this is an antisymmetric property, this one specifically. And this antisymmetry has to do with the idea of the sign of the area or the volume, because if you consider a surface like this, you can always define a positive, because a surface has two directions. If you take this as a surface, there is one opening like this, and there is another opening like this. So if you consider one of them to be positive, the other one is negative. Okay, so that's why there is this antisymmetry thing. And in general, this wedge product, no matter how many forms you take, it will always be anti. This is defined, the wedge product itself is defined as an antisymmetric product. Okay, so this is for differential 2 forms. Now what about differential 3 forms? Similar, just like differential 2 forms, you can define differential 3 forms as follows. so let's just call them 3 forms. And now let's say instead of xyz we turn our notations into x1, x2, x3 and so on. So it will be something like dx1, dx2, dx3, which will act on 3 pairs of vectors. Let's say w, x, y. These are 3 vectors, and again you will have some determinant like w1, x1, y1. I'm obviously jumping 2 steps, but you can easily fill them out using the previous example that we considered a few minutes ago. And you will have this w2, x2, y2, w3, x3, y3, like this. These are just determinants. And now what about differential 4 forms, 5 forms, 6 forms, or let's say differential n forms? How do you write those things? Just like this. And now comes the interpretation of this wedge product. So just like differential 1 forms, let's say you take dx, and what it does, it takes the vector and it measures the projection along this basis, right? This is the basis. Similarly, differential 2 form measures the projection of this volume, or so to say area. If you consider 2 dimensional, you can call it an area, but for the general case we are regarding this as a volume. So what this differential 2 form does is that it takes some pairs of vectors, and when it does, it's already considering the space or the object that is spanned by those vectors, and it finds out the projection of the volume along these bases. That means if it's dx dy, if you think of it as the cotangent space, then the component of dx dy will be your projection of the volume in the tangent space, because this dx dy, they are living in the cotangent space. So it's a bit hard to visualize, because usually we visualize the bases as a line, a one-dimensional thing, but here what is happening is that this dx dy, a two-dimensional thing, is becoming a basis. Okay, so this is a geometrical interpretation of these differential 2 forms. Now we want to move to differential n forms. We just want to see how to write them, and obviously before we move on to that, we want to state another thing, that let's say you have you want to have some projections of a differential 3 form. That means you are taking 3 pairs of vectors and you want to find out those projections, and at the end of the day you want to express that projections into a compact way using these differential 2 forms. So any differential 2 form, any differential 2 form can be written by the following. So this differential 2 form, let's say a12 dx1 wedge dx2 plus a23 dx2 wedge dx3 a31 dx3 wedge dx1, like this. You might ask, okay, what is happening with the other basis? That means dx2 wedge dx1 or dx3 wedge dx2, like this and stuff. So it's a very easy exercise to show that those things with the antisymmetry property can be absorbed into these coefficients. It's as simple as that. So that's why we try to maintain a cyclic order, so that we don't have to come up with a minus sign in between. And since dx wedge dx2, dx1 wedge dx2 is just minus dx2 wedge dx1, we want to absorb and simplify the coefficients as much as possible. So this is one way to see it. And if you are working with, let's say, n forms, that's the thing we wanted to see. If you are working with differential n forms, any n form can be written, any general n form can be written as the following. Okay, I shouldn't give the summation symbol right now. So let's say 1 2 3 n dx1 wedge dx2 dx3 obviously there is a wedge dxn, and there will be some cyclic terms like this.